(22 to 24). I'm really sorry about this, but soon as I saw a unit that was based on cyclobutadiene, I had no choice but to show you the depth and sorrow of my geek humor, which is unfortunately a type of humor it's there for life. You can't get rid of it, and it really sucks, but that's life. So I had to share that with you. Okay, so let's get to the questions. So the question is about retrocyclisation of cyclobutenes to form butadienes. And of course, this is butadiene because it has 4 carbons, 1, 2, 3, 4 carbons, and it's a diene because there's 2 alkene functional groups, so it's a butadiene. And it's retrocyclisation because to cyclize means to create a cyclic compound. So the going from right to left would be cyclization, to create a cyclic compound. And if you go to section 4.2, you'll see the Diels-Alder reaction, very classic cyclization reaction, which comes up on the real exam on a regular basis, reportedly, because of you know, the logic, the reasoning involved. It's not that you have to memorize anything, including for this passage as well. The other thing, some little things to mention. You notice that ACER has R1, R2, R3, R4. You're going to see that there are many different ways to label the R groups, the alkyl groups, to give you the impression that these could be different groups. And what these groups may represent can also change from exam to exam. Sometimes they are alkyl or aryl groups, meaning aromatic hydrocarbons or other hydrocarbons. But sometimes ACER will even say in certain circumstances R can be hydrogen. So they will have to define that for you. And also sometimes you'll see, you know, ACER will put primes instead. This is still just another way to label the R group, so R prime, R double prime, R triple prime, etc. So they can do it that way. Another way to label R groups is to use a subscript, but this is frowned upon in chemistry because it can give you the wrong impression as to the meaning. But ACER normally does this or this one. Actually, they use this one more often, so I guess they have a new organic chemist working for them. So okay, so then it talks about cyclobutenes to, which is this is a cyclobutene, to butadienes, can be thermally, and they show you the classic symbol for thermally, which means to add heat, heat energy, so delta, and then it says clockwise or anti-clockwise, and then it photochemically, and then they put lambda nu. That is a first year physics error. Student first year physics would pick that up quite quickly, because you know, energy of a photon, which is suggested by photochemically, is given by h, which is Planck's constant, times frequency. The other way you can write it, as ACER does, is the Greek letter nu, and I'm sorry, it's h and the Greek letter nu, so nu for frequency. That's all perfectly fine, but it's velocity of a wave, which is equal to lambda frequency, which you can also put as nu, and so very strange that they would put lambda nu, which is the velocity of the wave, instead of the energy of the photon, which is this. All textbooks will use this h nu, so it's just a little typographical error they must have had, resulting in rotating clockwise and other counterclockwise. Okay, so, you know, just in terms of understanding what's going on here, of course, the dark triangle in organic chemistry means that it's coming up towards you, and the broken triangle means it's going away from you. So R4 is coming up towards you, R3 is away from you, and then the other bonds are in the plane of the screen or paper or document. So it's in the plane, whereas this is up, coming out of the plane, and this is behind. So, and then there's these rotations that they're talking about, whether the rotation is in or out. So I'll try to take a special effects here to demonstrate what this is talking about. So, sorry about this, but anyway, this is best I can do. So this is a nail clip, apparently, and it's made in Korea. Look at that. I didn't even know. I didn't know they would make things like this in Korea. I thought it was only technology. But anyway, so let's say that this is R3 over here, and over here is your R4. So, you know, when you look at it on your paper, it looks like they're flat, but of course not. They're actually like this. Okay, what a difference, isn't it? So R3 is in the back here, and R4 is coming out towards you, and this would be the plane of the paper. So you see, it's quite a difference when you consider that it's really like this. And so when you're talking about R3 rotating inwards, that's what it means. It's truly rotating inward. When you talk about R3 rotating outwards, boom. It's like that. That's really what's going on. So this is the in rotation, and that's the out rotation, and that's all the special effects for today. Okay, so now going back to the passage, you're given a table, and now we can see what goes in and what goes out. The information also is telling us that this is indicating the activation energy. And of course, you know, you don't have time to think about everything for every question, but somewhere in the back of your mind, you should have this graph, because ACER sometimes has this graph on their exams, and they label it in one way or the other to see if you know what it represents. Of course, this is the reaction progress. That means you start with reactants, you end with products, and this is the potential energy. And so this is a situation where the reactants have higher energy than the products. So energy was released, given to the environment, and so we would expect the temperature would have gone up, and we would expect this to be an exothermic reaction as energy exits, and you end up with more stable products here. And so this is the delta H change in heat energy from the reaction to the product, and it would be negative in an exothermic reaction like this. And here is the activation energy. This is the energy to get the reaction to be able to go. Once it gets up to the top of the hill, easy to go down the hill, but you have to give some energy in order for the reaction to take place. And so that's the activation energy. And of course, this is the transition state up here as the chemical goes from what it was to what it will be. Okay, so just in one of the notes, it says, assume only the dominant product is formed. Hello, it's Dr. Ferdinand from the future, relative to when this original video was made. By the way, the future is great. There was a pandemic with masks and vaccines, but everyone got along swimmingly, moved forward, and now there is sunshine and happiness and flying cars. Now back to retrocyclisation of cyclobutenes to form butadienes. Some students left comments unsatisfied with my previous efforts. Nail clip ambivalence, the squeaky wheel gets the oil. I also noticed that some students were able to get one or two questions correct by luck, essentially. So here goes a more comprehensive work solution. First, perspective and strategy. There are 3 questions in this unit, which means according to the new digital GAMSAT timing, you have 2 minutes per question in section 3. So prior to 2020, and even in ACER's current GAMSAT practice materials, they still use the old timing of 1.5 minutes per question in section 3, but you should practice with 2 minutes per question, as it is the case with the current exam. So this unit should take 6 minutes. However, we have and will discuss techniques for this exam to solve some problems in under a minute. That bank of minutes pays off in a unit like this. Basically, the first time you see a unit like this during a real exam, if you believe that it is too involved for you, guess, write down the question numbers on your A4 scratch paper, which is provided to you at the test center, and then come back to this unit when you have 10 or more questions left, and 10 or more minutes left, and address each issue systematically. If you are an organic chemistry student, then you should fast forward or use the settings on this video to increase the speed. I'll sound like a chipmunk, but you'll save a lot of time. Okay, so let's start with the basics. So here is an advanced drawing of a clock to remind you of the relevant turning directions, just as you would for torque forces. So here's a clock, and the hands of the clock move in this direction, so that means this is the direction of clockwise. And if you go in the opposite direction, that is anti-clockwise or counterclockwise. Okay, so for the rules, I wouldn't say that for every unit you're going to write down the rules, but you will see throughout the Pink booklet there are some times where I write down the rules. And there will be some times for some students that it's helpful to write down the rules on the scratch paper during the real exam. So I've written the rule for delta, which is thermally, which means heat energy is provided, and photochemically, which means photon energy or light energy was involved in producing a chemical reaction, and that's symbolized by H nu. And so according to the unit, if you do it thermally, then both N groups move clockwise, and this is the example provided in the unit, or both can move anti-clockwise. And we'll discuss this in a couple of minutes. And then photochemically, one N group rotates clockwise and the other N group rotates anti-clockwise. Let's look again at this example. We have graduated from a nail clip to plastic balls. Okay, so yellow is R2, purple is R4. R2 and R4 are projecting towards you. Now notice, for the cyclobutene, these groups are really like this. The top group eclipses the group in behind if you are looking at it from above. But ACER draws it just off to the side a little bit, almost as if it were staggered. Nonetheless, R2 and R4 are clearly towards you, and R1 and R3 are clearly in behind. For now, just focus on R2 and R4, the yellow and purple, and notice how they will move indeed clockwise. So it started up here and then clockwise motion. Of course, all groups are moving in a clockwise direction simultaneously. And in so doing, the yellow group moves in and purple moves out. And now for a different point of view. You know how for double bonds, when groups are on the same side, they are cis. It's the same thing for a cyclic structure. If groups are on the same side of the cyclic structure, they are cis. You can also say Z. Z for same side. So that those are the groups that are on the same side. So yellow and purple are on the same side. Notice that yellow moves in, purple moves out. So another way of thinking about it is that when both move in the clockwise direction, the top group, for example, the two groups on the same side, the two top groups, one group moved in, yellow, and the other group moved out, purple. So this is a different way to summarize what is happening. Of course, in all these instances, black symbolizes the carbon atom. And that's the carbon atom that is here, here, here. In our rule for thermally, we can have clockwise movement or both can move anti-clockwise. Now notice that when both move anti-clockwise, again, for yellow and purple, one moves in, which is R4 in this instance, and yellow moves out, which is R2. So whether both move clockwise or both move anti-clockwise, we have the same thing happening for the two groups that are Z. One goes in, one goes out. Now let's look at photochemically. Photochemically, one moves clockwise and the other one moves anti-clockwise. Okay. So if this moves clockwise, this one is moving anti-clockwise. And now we have R2 and R4 on the inside. Now if this group moves clockwise and this group moves anti-clockwise, then we have R2 and R4 on the outside. So to summarize, both groups that are on the same side will either move in or both will move out. Both move in or both move out with photochemically promoted reaction. Okay, so that's it for rule number 1. Now for rule number 2. I got a little bit excited and I put the absolute value symbol here, which is discussed in GAMSAT Maths Chapter 1. But I do need to explain that there's two different ideas that I want to present to you. Idea number 1 is the simple one that if the value is positive in the table provided in the passage for the activation energy of the end group, if the value is positive, then there is a preference for in rotation, and if the value is negative, then for out rotation. So those are the values from the table and have nothing to do with the absolute value. However, the reason I put the absolute value is because ACER says the carbon for which the magnitude of the sum of the En, E out values, magnitude refers to the absolute value. Now, why is that important? It's important because when you look at the table, the higher value is going to be dominant. So 14 for the methoxy group and 10 for chlorine means that if they are in competition, methoxy group wins and will move in. So in this case, it is the higher value that wins. But what about NO2, which is -4, and CHO, which is -5? If these were in competition with each other, which would win? NO2 is the higher number, but CHO is the higher magnitude, which means the absolute value. And ACER stuck in that word magnitude so that we can understand that the more negative a value is the greater the drive to go out. And so the dominant value wins. That's always easy to understand with positive values, but now it's also clear with negative values. Negative wins to go out. So now we will use the 3 rules to answer the 3 questions. For question 22, we have chlorine, which is +10, hydrogens, each 0, and the cyano group, which is -2. The highest number is 10, of course, but it's also the greatest magnitude. So, for example, had the cyano group been -12, then it is a greater magnitude than Cl. So then we would say that at -12, the cyano group has a greater drive to go out than Cl has to go in. But as it stands, Cl is the highest number, and so it has the greatest drive to go in, and nothing else compares. If one of the four groups was the methoxy group, which is at 14, then under that situation, if it was Cl versus methoxy, both connected to the same carbon, then methoxy would have the greater drive to go in, and then Cl would end up out. But that is not the case here. Okay, so let's consider some possibilities. Let's imagine that green is chlorine and purple is the CN group. Chlorine dominates and has a drive to go inside. The CN group is happy to go outside. And of course, that was an anti-clockwise movement. And so if this is thermally, then the two hydrogens would move like this, also anti-clockwise. Now let's consider that the purple group is hydrogen. Green is still chlorine. Of course, chlorine dominates. And no matter where the cyano group is, whether it is yellow or blue, it has no choice because chlorine dominated. And if this is thermally, it has to move in this direction. Likewise, for photochemical reaction, if chloride is green, it doesn't matter what purple is, chlorine will move inwards because it is dominant and has the highest magnitude. And no matter where CN is, if CN is purple, it happily moved out. If CN is on the other side, either yellow or blue, it has no choice because chlorine just moved anti-clockwise, so this side must move clockwise. Thus, either thermally or photochemically, chlorine moves in both cases. And so 22, the answer is A. Always rotate in. And now on to question 23. So here we have chlorine, which is plus 10. We have hydrogen, which is 0. And now we have CF3, which is minus 1. And this time we know where each one is placed in the molecule. Some students looked at the difference between chloride and hydrogen and correctly assumed that the activation energy difference is 10 because chloride is 10 and hydrogen 0. But some students looked at the difference in energy between chloride and CF3, which has 10 and minus 1, and they decided it was 9. But this is En minus E out, as is common in general chemistry, products minus reactants. So you can't do 10 minus 1 is equal to 9, because that's not the difference. Because what if this was 10 and another one was 1? What would you say the difference is? If it was plus 1, you would say it's the difference between 10 and plus 1 is 9. So the difference between 10 and minus 1 is 11. Or the other way of doing it is 10 minus 1. And thus, this is the side that has the greater energy difference and will move first. And because it is photochemically, the other group will move in the opposite direction. And the other way to think about it is that the two groups that are on the same side, the Z groups or cis groups, both move in or both move out. So let's have a look. Okay, so now we are photochemically promoted, one clockwise, one anti-clockwise, and the group on the left has the greater energy difference, and we've already confirmed from question 22 how much chloride wants to move in. And now in question 23, it has an even greater drive against CF3 than it would have with just hydrogen. So chloride moves in, and that's a clockwise movement. Photochemically means that the other group moves in the anti-clockwise direction. The other way to look at it is that both groups moved in, and thus we have the answer C. And I would just like to draw your attention to these double bonds here in, of course, the butadiene component of the molecule. I just want you to understand that the double bond is what locks these groups into place. If there was no double bond here, if this was a single bond, then there would be free rotation and there would be no unit on this issue, because these groups would always be rotating around and round along the single bond. That is called conformation. But because it's a double bond, it means that once this reaction takes place, these groups are locked into position. This carbon atom is at the center of a flat triangle, trigonal planar, whereas this carbon is in the center of a three-dimensional structure with one group coming towards you, one away from you, and one in the plane of the paper or computer screen. Okay, so let's move on to question 24. So, following structure. So we have the methoxy group, which is plus 14. We have chloride at plus 10. We have a methyl group, which is plus 7. So we have 3 positive groups that are driven to move inwards. We have CF3 at minus 1, NO2 at minus 4, and CHO minus 5. It is photochemically promoted, and we are asked about which circumstances would the R group rotate in. We already saw that the CN group is minus 2 and thus wishes to go out. So I know what a lot of students would have done. They would have looked at how many positive groups are there. 1, 2, 3 positive groups, and they would have chosen that as the answer. And although the answer is indeed 3, 24C, I'm sad to report it's a little bit more complicated than that. Before we talk about the actual rotations for photochemically, just in case anyone got confused about the way that it was written as NC, which does not stand for Newcastle or New Caledonia, but rather it is the cyano functional group, which can be written as CN, NC, or like this. After all, the diatomic molecule nitrogen, which forms 78% of air, 21% being oxygen, and about 1% being various other gases, is a molecule that looks like this. And over here is just a reminder that you might see the hydroxyl group written as HO or OH, depending on style and bonding patterns. Okay, so now let's consider the various possibilities for the rotations. The purple is the hydrogen group in behind, and the light blue is, well, let's start with the methoxy group, with its activation energy of plus 14. It is the highest number, it is the greatest magnitude, it is driven to move in. And then, because it's photochemically, we have both top groups moving in. But we were not asked about that aspect. If blue is chlorine, again, because of the value 10, it moves in. If blue is CH3, it is the highest number of the 4 groups, meaning compared to hydrogen and the cyano group, and so it's driven in. Now, CF3 at minus 1, it has a small drive to move out. But let's say the cyano group is green, and it being minus 2, which is a greater magnitude than minus 1, it is driven to go out. And because it's photochemically, CF3 must move out also, because in our rule, both in or both out. NO2 at minus 4 moves out, and because it's photochemically, CN also moves out. CHO minus 5, CHO like NO2, have a greater drive to move out than the cyano group has to move out. So CHO moves out, but because it's photochemically, okay. The cyano group also moves out. Now, if you really understand this, then you can pause the video and try to decide what the answer would have been if instead of saying photochemically, ACER had said thermally. So let's consider thermally. For methoxy, chlorine, and methyl, it's the same story. This is going to move in. And in each of those cases, this moves out. Because in our rule, the top groups, one move in, one move out. Now, what if it's CF3 at -1? Well, the cyano group is -2, the green, and it has the higher magnitude. So the cyano group moves out. If this is thermally, then CF3 is forced to go in. One in, one out. Both moved in this anti-clockwise direction. And so if the question was thermally promoted, then the answer would have been 4. But the answer is 3 as it stands, 24C. And you can see some cross-references in the book, ORG 4.1, 4.2, for activation energy in graphs, Chem 9.5, 9.7. And if you want to do more practice questions like this in the new Master Series, Chapter 4, questions 24 to 28, 38 to 40, Chapter 6, 26 to 27, Chapter 7, question 40, Chapter 11, questions 24 to 25. Okay, so let's take a quick peek at the new Master Series, GAMSAT Organic Chemistry by Gold Standard. And this is available in bookshops, libraries, and also online as an ebook. So the table of contents is color-coded, where yellow is for high importance chapters, green for medium importance, and blue for low importance chapters. These aren't opinions. These are percentages based on actual ACER GAMSAT practice questions. Basically, which official questions actually required assumed knowledge from a particular chapter. The book has 14 chapters divided into 5 sections, starting with carbon, of course. Organic chemistry is the chemistry of carbon. So molecular structure and stereochemistry. Then carbon meets hydrogen, and these are the hydrocarbons, alkanes, alkenes, aromatics. And then carbon and hydrogen meet oxygen. Then they meet nitrogen. And finally, how do we know what molecules actually look like? So separations, purifications, and spectroscopy. Each chapter starts with what you need to memorize for this exam specifically, what you just need to understand, and what is the level of importance of this specific chapter. Again, this is not an opinion. This is based on data from the 440 multiple choice practice questions ACER has made public. And then there are exercises and exercises. It's not just a book of learning and content. It has evolved into a workbook. Of course, every chapter has GAMSAT level practice questions, detailed work solutions, and there are spoiler alerts that detail which questions from ACER's practice materials specifically require assumed knowledge from this chapter. That way, you do not have to trust our percentages. You can confirm them for yourself. And then every chapter has a chapter checklist to ensure that you are meeting your objectives. And one last thing I'd like to show you. A reaction that you are very familiar with now. Here is the cyclobutene, two groups on the same side, photochemically promoted, and the two groups move outside. Again, the cyclobutene, the two groups on the same side, thermally, one group moves in and one group moves outside. Easy stuff for you. Of course, this is not to be memorized, but organic chemistry challenges your geometric reasoning and your pattern recognition. You've made it this far, so keep up the good work.